Good evening. My name is Michael Potter. It is approximately 21:27 on 14th of September 2020, and we're going to talk about Case Connection 3, dealing with lipid metabolism and some of the disorders with lipid metabolism. Um, just a quick exogenous, endogenous, and secretory overview. We have our exogenous lipids coming into the small intestine and being broken down by bile salts and acids and moved into the intestinal walls, which then the intestinal cells will end up ultimately secreting a chylomicron that is containing triglycerides and cholesterol. And this will go into the lymph system, where the lymph begins the maturation process of this chylomicron, with the ApoB48 being attached. ApoB48 is going to be important later when it interacts over here in the liver. So with all lymph, it is eventually dumped into the circulatory system, and the circulatory system contains HDL particles. Will interact with this um, chylomicron to fully mature it, attaching an ApoB and ApoC2. We'll see the ApoC2 will come and interact with this LPL, or lipoprotein lipase, which is attached to the intestinal wall, or the circulatory system walls, and allow for the interaction of the chylomicron with extrahepatic tissue. In this case, this is adipose tissue, but all extrahepatic tissue that requires the cholesterol and triglycerides, which are important members of cell membranes and other building blocks. So we lose the ApoC2 and some of our triglycerides and cholesterol, and this chylomicron remnant is then moved back into the liver. The HDL is again interacted with and dropped off that ApoE again, and we pull it into the liver for hydrolysis and metabolism. That's the path of our exogenous. We're not going to deal much with that until a little bit later, but for now, let's just move on to our first case study, and that is going to be involving a 53-year-old male with a medical history of obesity and borderline diabetes. The patient does present with an abnormal liver enzyme test, as you can see. His AST is 106, which is almost triple the upper range of normal, with his alt being about 118, which is more than double the upper range of normal. Normal bilirubin is going to indicate there won't be any jaundice in this patient. We're going to see it in the eye, the sclera of the eyes, or the membranes, and not the fingertips. We'll see it in the skin, because that's a inability to get rid of bilirubin from the liver. This normal bilirubin's going to just be normal skin. So the patient had a liver ultrasonography. It confirmed mild hepatomegaly. With this hepatomegaly, we also see on the ultrasound that there's increased vascular blurring, with consistent with fatty infiltration. That's fatty deposits left within the hepatocytes. So leading us to believe it's non-alcoholic fatty liver disease. Non-alcoholic just indicates that our patient here does not imbibe alcohol excessively, routinely. May have some drinks, but he's not considered an alcoholic. So moving on, we're going to take a look at our first question, which is under normal circumstances and conditions, we're going to describe the metabolism and maturation of VLDL particles. We're going to have within the cells, and then we're going to move out into the circulation. So first within it, VLDLs are formed within hepatocytes, or liver cells. The ApoB100 is going to be our skeleton for the VLDL. That's what's going to allow for lipids to be attached. Microtriglyceride transfer protein, or MTP, affixed to the initial lipids. However, further lipids are going to be attached via other processes. These lipids are found from either endogenous sources, meaning they're created from the acetyl-CoA, or the free fatty acids, which are taken from circulation. First, we're going to take a look at how our fatty acids, we have them synthesized, and they move into the ER lumen. Within here, we're re-esterified and lipolysis, where an MTP takes these lipids and attaches them to our ApoB100 protein, which has been expressed from our ribosomes here, and moved into the ER. This is our first regulatory insulin step right here, where insulin is able to stop this ApoB100 from being created within the ER lumen. And from here, we have our initial VLDL2 molecules with triglycerides and cholesterol being obtained, which are then going to be secreted from the ER via COQ2 vesicles and going to be uptaken into the Golgi, where our second insulin step does not allow for the full maturation to VLDL1. And so this is going to be our second insulin regulation, which we'll talk about a little bit later for our disease. However, both the VLDL2 and the VLDL1 are ultimately secreted and, again, interact with the HDL or paving the ApoC2 and ApoE to be considered mature VLDL. So within our circulation, again, we talked about being excreted with our triglycerides and our cholesterol esters and cholesterol, interacting with HDL, taking some of HDL's cholesterol, donating triglycerides. Again, with these cholesterol esters being pulled in, it's also attaching the ApoC2 and ApoE. We are coming around, we're interacting with the lipoprotein lipase, pulling off some of this cholesterol esters and triglycerides, and ultimately being brought into the cell and we moved into a IDL or intermediate density lipid or VLDL remnant with significantly less triglyceride per percentage, and moved back into the liver and unesterified and broke down. Then we move into the LDL. We have LDL coming back out and being accepted and with donating cholesterol down here. But ultimately, the process for the VLDL is pretty simple, similar to the rest of our fatty metabolism. Here is a little picture of a healthy liver versus a fatty liver. You can see our healthy liver is very vascular and very rich in red blood and the red iron, the red being contributed by iron. Our fatty liver is significantly yellow. It's got fatty deposits within the hepatocytes, and they're just unable to look pretty red. So here's our risk factors for our non-alcoholic fatty liver disorder. Our first ones are going to obviously be lifestyle, obesity, diabetes, insulin resistance, hyperglycemia, all end up being attributed to diet. Although some genetic factors can predispose you to a few of these things, for the most part, poor life choices are going to be our significant contributing factors to this. And genetic factors, which we will discuss, failure to express protein effectively, incorrect insulin, things like that can end up moving us towards this fatty liver disease as well. So excess dietary lipids in the adipose tissue are increasing free fatty acids, which are available in circulation. These free fatty acids are being brought into the liver, and which increase the production of VLDL. VLDL regulatory step is not what one would assume, which is the creation of the ApoB100 skeleton, but rather the regulatory step is going to be just the free fatty acids available and our lipolysis or our lipid generation via acetyl-CoA. If that's available, we're just going to continually build VLDL. Ultimate fate of VLDL being converted down to LDL. The LDL being brought into the cell to be broken down and excreted in the excrement. However, as this happens, we constantly are creating VLDL. We're exporting it. It's being secreted out. It's being circulated. More LDL is coming back in, and the liver is ultimately unable to keep up with the influx of these lipids. The VLDL can't get rid of it fast enough. The LDL is coming in faster, and we have a formation of these stores of fat within the hepatocytes. When this happens, and we continually have this happen over years and years. We built it up to a point where the liver is just unable to handle it. We have some further disorder down the line, ultimately ending with cirrhosis and liver death. So now we move on to the sort of genetic factors. Insulin suppression, as I talked about earlier, were the two insulin level regulatory steps. If those regulatory steps are not there, we constantly are going to be pushing out this VLDL into the system. And as we talked about, it's a positive feedback loop here. If there's fatty acids available, we're kicking it out. As we kick more out, we get more LDL back. We get more LDL back. We create more fatty acids, and we just down the hill we go. So anything that degrades, the process for degradation of and excretion of the lipids are going to cause the buildup as well, and our enzymatic expression. Specifically, I want to point out the MTP. If our MTP is decreased expression, unlike the rest that are this positive feedback loop of constantly bringing LDL back in, this is actually going to just cause a buildup because we're unable to create the VLDL. There's some very serious results of this, this decreased expression of MTP, and almost generally cause liver failure very early in life, but ultimately creates it so that the ApoB100 skeleton is unable to have the first lipids attached to it. If the first lipids are not attached to the skeleton, further down the road, the downstream processes aren't able to attach more lipids, and we have buildup in our hepatocytes again.